Hello students, I am Sandhu, Assistant Professor, Department of CSE, MITM. So, in the today's session, we will discuss about the design of fast adder. Before we are going to this topic, first see what is ripple carry adder. To overcome the disadvantage of the ripple carry adder, we are using the fast adder. It is also called as look ahead adder or parallel adder. Okay, first see what is the ripple carry adder. Say for example, xi and yi. So, these are the two inputs xi or two bits xi and yi. You will get the sum, it is si. So, the carry it is taken from the previous column, it is ci. It is also called as carry in. Okay. So, the next is the carry it is generated from this column and it will be propagated to the next row. It is called as Ci plus 1 or it is called as carry in. Carry out. So, this is Ci, it is called it as carry in, and the Ci plus 1 it is called it as carry out. Okay. So, in the arithmetic and logic operation, in the ALU arithmetic and logic operations, we are using AND gate, OR gate, NOT gate and XOR gates. So, compared to multiplication and division, the addition and subtraction circuitry is simple. That means multiplication and division circuitry is bit complex than the addition and subtraction circuits. Okay, and the addition and subtraction circuit is bit complex than the logic circuits. So, in the logical operations, you are doing the operation for single bit or you are applying the operation for individual bits, right. So, in that case we need only the combinational circuits to perform the logical operation and it is bit simple. In the addition and subtraction, we need extra signals. That extra signal it is called it as this carry or borrow signals, right. Here Ci and Ci plus 1 it is called it as carry signal or borrow signals. Okay. Take an example 0 plus 0. 0 plus 0. So, in that case, what is the output? What is Ci value and what is Ci plus 1 value? So, initially the Ci value it is 0, it may be 0. So, in that case the Si value is 0 plus 0 is 0 only. Okay. So, the next is Ci plus 1. So, by adding these two numbers, the carry it is generated from this column, again it is 0. Okay. Take another one example 1 1. So, in that case the Ci initially it is 0. Okay. Usually we are using Ci value in the 2's complement addition. So, in that Ci value it will be 1. Okay. So, otherwise it is Ci value it is 0 initially. Okay. So, the next is 1 plus 1, the answer that means Si, the sum is 0 and the carry is 1, that means it is a C out value, that is C out is equal to 1. Okay. So, you can write this in the circuits, you can write this in the full adder block diagram. Here this is the full adder and we have two bits, right. So, that is xi and yi. Okay. So, in this xi and yi, this is Ci value and the output or C out value from this block it is Ci plus 1 and the sum of this block it is Si. So, this block it is used for only the 2-bit addition, 1 plus 1, 0 plus 1, 1 plus 0, 0 plus 1, like that. Okay. So, we have 4 bits. So, in that case, we have 4 bits. In that case, take an example for that. It is 0, 0, 1, 1, 0. Okay. So, the next is 1, 1, 0, 1. Here this is x and this is y value. This row is x and this row is y. Okay. So, here it is, this is x0 and y0. Okay. Initially C0 will contain value 0, right. So, this is the C in value, 0 plus 1. What is the answer? What is the sum? That is S0, it is 1. This is S0, right. So, what is the C out value for this column? That means C out means it is a carry generated from this column and it will be propagated to the next column, right. So, here 0 plus 1, the answer is 1, that means S0 is 1 and the carry Si plus 1 is 0. Now this 0 it will become the C in value, that is Ci value. Here it is a C1. So, add these 3 numbers 0, 1, 0. So, again S1 value is 1 and the answer is, or the output carry out is 0. Now, this carry out value, that means C2 value, it will become the C in value. Now, 0, 1, 1. So, if it is 1, 1, the answer is 0. That means S2 value is 0. So, then the carry is 1. Now, the C out value is 1. So, in the next column, this will become the C in value and 1, 0, 1 and the answer is 0 and carry 1. Now, this is C4, right. This is C4. This is C0, this is C1 and C2 and this is C3. Okay. So, based on this example, you can write the full adder block here. So, this is for first column and for the next column FA. So, this will become 0, 0 and this is C0 and this is S0 and for the next one it is 1. The carry for the next column it is C1. Okay. So, the next is the second column, it is x1, y1, the answer is, or the sum is S1 and S2, carry is S2. Now, this carry S2 it will become the carry in for the next column. Now, FA, this is x2, y2 and sum is S3 and the next is C3. Next is FA, S4, X3 and Y3. Okay, sorry, it is X2, S2 and S3 and the last carry it is C4. This is the ripple carry adder. So, write down the circuit diagram for this ripple carry adder. Here the sum function is xi XOR of yi and XOR of ci. This is the xi, yi and ci is the function, right? Xi XOR of yi XOR of ci. By using this you can generate the sum, okay, in the ripple carry adder. So how to generate the Ci plus 1? This is Ci plus 1. So for this step, this is Ci plus 1. Okay. So this is Xi Yi plus Xi Ci plus Yi Ci. So this is the function, sum function and the carry function. Okay. Now write the logic diagram for this. So the logic diagram for sum, it is a XOR of X, Y and C. So here XOR will contain 3 pins, right? Okay. It will contain 3 pins, that is Xi, Yi and Ci. Okay. The output from this, it is Si. Okay. This is for to generate the sum. Okay. So the next is for carry. Here we are using AND gate and this is OR gate, right? Okay. Here we need three. Here we need 3 AND gate. Okay. So this is Xi, Yi, Xi, Ci, Yi, Ci. Okay. Next you need to use OR gate to connect these 3 pins and this is the Ci plus 1. Okay. So here in the sum we have only one OR gate, right? We have only one OR gate. So here we have only one level. So that means to get the Si value we need one XOR gate delay. Why? To get the Si value we need one XOR gate delay. So likewise here, so this is the level 1. Okay. So this is level 2. This is level 1 and level 2. So in that case, to get the Ci plus 1, so we have 2 levels. So we need 2 gate. Here we are using both AND and OR gate, right? AND OR gate. So we need 2 gate delay. So this is for block 1. So in 4-bit addition, in the ripple carry adder we have 4 blocks, right? 4 full adder blocks, 4 cells, right? So in that case for S, to get the S4, that is the last sum, right? Say for example S0, S1, S2 and S3 in the previous diagram. So to get the S0, S1, S2 and S3 we need 1 into 4. So that means we need 4 gate delay. Okay. Likewise, so for this we have N. We have N, Cn. To get the Cn value we need 2 into N gate delays. 2N gate delay. So in the previous example, yes, 2 into 4, that means we need 8 gate delays to get the Cn value, that means C3 value. So, but we need Cn plus 1 also, right? So, in the previous example it is Ci plus 1. So, in that case 2n plus 2 gate delay is required to get the Cn plus 1. Okay. So, in the ripple carry adder, so to get the Si value we need 1 XOR gate delay. To get the Ci plus 1 we need 2 gate delays. So, likewise we need Cn. So, in that case 2 into n, that is 2n gate delays is required to get the Cn value or Ci value, or for Ci plus 1 we need 2n plus 2 gate delay is required to get the Cn plus 1. Okay. So, this is the main disadvantage of the ripple carry adder. To overcome this we use carry look ahead adder or parallel adder. It is also called as the fast adder. Okay. The next topic is carry look ahead adder. So, in the previous example, to get the C1 value you must need C0 value. To get the C2 value you must need C1 value. That means it is depends on the previous carry. It dependent on the previous carry value. So, that is also disadvantage of the ripple carry adder. So, in this carry look ahead adder the addition is done parallelly. That is why it is also called as parallel adder. Okay. So, here the sum is, as we know that it is Xi XOR of Yi XOR of Ci, right, and the carry I plus 1 is equal to Xi Yi plus Xi Ci plus Yi and Ci, right. You can rewrite this formula as Xi Yi plus C is common here, remove it out, Xi plus Yi into Ci. Okay. So, in the carry look ahead adder, this is Gi plus Pi Ci. So, here Gi is nothing but generate function. It is a generate function, and Pi is the propagate function. It is a propagate function. Here Gi is the generate function and Pi is the propagate function. Here Gi is nothing but Xi Yi and Pi is nothing but Xi plus Yi. Okay. So, here we need one AND gate for Gi and one OR gate for Pi and one XOR gate for Si. Okay. So, this is carry function and this is the carry function and this is sum function. So, we rewrite this carry function into Gi plus Pi Ci. Here Gi is the generate function and Pi is the propagate function. So, for this we need one AND gate for Gi, one OR gate for Pi and one XOR gate for Si. Okay. Now, write the logical diagram for this. Say for example, we have X and Y value, X and Y, Xi, Yi, by using AND gate here, right. By using this AND gate, you can generate the Gi function. You can get the Gi function. Okay. In the same level, by using the same input, so by using OR gate, we will get the Pi value. Okay. So, add C for this, Ci for this, and add this Gi function and use OR gate, again you will get the Ci plus 1. So, in this example, this is in level 1, this is in level 2, this is in level 3. So, that means here we need 3 gate delay to get the Ci plus 1, but in the previous example we need only 2 gate delay, right? But here we are doing parallel addition. Okay. So, yes, here we need 3 gate delay to get the Ci plus 1. Okay. So, for some it is again Pi, Xi, and here for the practical purpose we rewrite this Pi as Xi XOR of Yi. We rewrite this as Pi is equal to Xi XOR of Yi. So, in that case Si is equal to Pi XOR of Ci, right. So, in that case we need plus 1, add plus 1, that means we need 4 gate delay to get the Si value. Okay. So, we need 4 gate delay to get the Si. So, now write the, so by using this formula Si is equal to Pi XOR of Ci. So, we rewrite the logical diagram here. We rewrite Ci plus 1 is equal to Gi plus Pi Ci, right. Yes, now we rewrite this as, this is same Xi Yi and this is Gi. Okay. So, the next is by using the same input XOR you will get Pi, and by using this again XOR Ci you will get Si value. So, this is the logical diagram for Si. Okay. So, here it is called it as bit cell. Fully we are call it as bit cell or B cell. Here we have 1 AND gate and 2 XOR gate. So, here we have generate function, propagate function and sum and the carry. Totally we call it as bit cell. So, by using this you can add the numbers. So, this is for 2 bits. Okay. Now write the 4-bit carry look ahead adder. Okay. Now, write the diagram for 4-bit carry look ahead adder. Okay, this is B cell. So, in the carry look ahead adder we are using carry look ahead logic. Here this is the carry look ahead logic. Okay. So, in that this is X0 and Y0. X0 and Y0, this is bit cell. So, inside this we have 2 XOR gate and one AND gate. Okay. So to get the Ci plus 1 we need 3 gate delays, and to get the Si value we need 4 gate delays. Okay. Okay, here we have C0 value. So if we are doing in the 2's complement addition, so you need to add 1 to the 1's complement result, right? So in that case the C0 it will be 1 or else it is 0. Okay. So this is also send it to the carry look ahead logic, and you will get the answer, that is S0, and we get two functions, that is G0 and P0. G0 and P0. So like that. So the next is second B cell, second bit cell, this is X1 and Y1, and the sum is S1, and the propagate and the generate function is G1 and P1. Okay, so yes, we get G0 and P0, and we have one more, right? So by using these two numbers, the logic carry look ahead logic, it will generate the C1. So that will be sent to the next column. This is C1. Again after this we get this value C2, and this is the next bit cell, and this is X2 and Y2, and this is S2, and what is the propagate and generate function here? It is G2 and P2. Okay, so the next you will get, by using this carry look ahead logic, we will get the C3, and this is your fourth cell, fourth bit cell, X3 and Y3, and this is the S3 and this is P3 and G3, and the last you will get C4. This is the diagram for 4-bit carry look ahead adder. This is carry 4-bit carry look ahead adder. Here we are adding 4 numbers or 4 bits. Okay. So okay, after this, yes, how it will be do the addition and carry function parallelly? We don't know, right? Okay, take an example. Yes, already we have C0 value, right? C0 value. So you need to calculate the C1 value. How? So for C1 it is G0 plus P0 C0, right? Once we get the P0, G0 and C0 value, so the next step is done parallelly. Okay. Next is C2. So for C2 it is G2 plus, sorry, G1 plus P1 C1, right? Yes, we know the C1 value, right? Here. Yes. Now G1 plus P1 C1 is G0 plus P0 C0. So now we will get G1 plus P1 G0 plus P1 P0 and C0. Only we need C0 value. Once we get the C0 value, all the B cells, it will calculate, it will add the numbers parallelly. Okay. So who will help to add the numbers parallelly? Yes, here carry look ahead logic, it will help the cells to add the numbers parallelly. Okay. So yes, we need C3. How to get C3? Here it is G2 plus P2 C2. Again C2 is here. So G2 plus P2 into G1 plus P1 G0 plus P1 P0 C0. Again multiply these, we will get it is G2 plus P2C1 plus P2 P1 G0 plus P2 P1 P0 and C0. Okay. Okay, for C4 again it is G3 plus P3 C3. C3 is here and find out the function here like this. Okay. So here this will perform the addition, here it will perform the addition parallelly. Okay. This will done by carry look ahead logic. This is 4-bit carry look ahead adder. So yes, by using this diagram you can also write the 16-bit carry look ahead adder. So that means you need 4-bit cells. Here this B cells is nothing but single bit. Okay, like that we need 4 bits, 4 cells to write the 16-bit carry look ahead adder. Okay, say for example, okay, in the next example take only 8-bit carry look ahead adder. So in that case okay, to perform all these operations it requires only 3 gate delays. For carry it needs only the 3 gate delays and 4 gate delays to perform to get the SI value in all the stages total. Okay, it is a total delay. So totally we need in the carry look ahead adder only we need 7 gate delays to get the SI, final SI and CI value, CI plus 1 value. Okay. Okay, now 8-bit carry look ahead adder. So in that case, yes, this is the carry look ahead logic. This is carry look ahead logic and this is the 4-bit cell. Here, so totally we need only 2, right? 4-bit cell. For 8-bit look ahead adder we need only 4-bit 2 cells. Okay, inside those 4-bit cells we have 4 B cells. Okay, B cells is nothing but only bit cell, right? It contains only 1 bit xi, yi. Okay, but here in the 4-bit it is x 0 to 3, y 0 to 3. Okay, so please remember the previous diagram. Okay, okay, here xi 0 3, yi 0 to 3, we will get the sum. It is s 0 to 3 and this is, say for example, this is p0 of I and this is g0 of I and this is c0. Okay. Okay, here it is C0. Okay, so the next you will get the next carry is C4. Okay, so inside this again we have 4 inputs x 4 to 7 and y2 4 to 7 and s it is 4 to 7 and we have P0, P1 of I and G1 of I, and you will get C8, carry 8. So this is 8-bit carry look ahead adder. Yes, once we know this, yes, you can easily write the 16-bit carry look ahead adder, right? 16-bit carry look ahead adder. So for that, again you need to extend it. Okay. Again we need 4-bit cell. So here we get the C8, and the next is X8 to 11, Y8 to 11, and S8 to 11, and the next generate and propagate function, that is G2 of I, P2 of I. Okay, sorry. So the next is, again we need 4-bit cell, 2 inputs and 1 carry, C11. So X12 to 15 and Y to 12 to 15. So output is, sum is S12 to 15, and propagate and generate function G3 is of I and P3 of I. Okay. So you will get the carry C16 here. Okay, this is 16-bit carry look ahead adder. So inside each blocks you will have 4-bit cells. This is the carry look ahead logic. So here it will generate the carry and it will propagate the carry here. So by using this we will get G0 of I, P0 of I. This is the carry and generate function. It is generated by the carry look ahead logic. So again you can easily write the 32-bit carry look ahead adder also. Okay, you need to extend this till 32-bit. Okay, this is all about the carry look ahead adder. So here generate and propagate function is very important here, and here the addition is done parallelly. That's why it is also called as parallel adder. So this is very important and bit easy also. Thank you.